Did y'all enjoy the wellness day yesterday? I drove back to Yukon because I didn't want to sit here all day. And then I drove back this morning and I was almost late. I had to stop at Carl's Jr. because I was hungry. So, if no one has any questions over what we discovered last time, let's move on to standard deviation. So, let me get there in my notes. So, like I kind of briefly introduced last time at the end of class, the standard deviation is, does anyone know what it is? The what of the variance. The square root of the variance. So, then just applying the square root, we have sigma is equal to the square root of sigma squared. And S, which is the sample standard deviation, is equal to the square root of the sample variance. What the heck is that? What's up? I gotcha. Idea. Come on, stupid mouse. I'm gonna kill that person if they don't stop. Or whatever it is. Is that better? Okay, there we go. Sorry. So, shut up, person. So, back to the example that we talked about last time with this little data set, right? Where was it? Here. We want to find the standard deviation for the population and the sample. So, recall that the population variance was equal to 4.24. So then the population standard deviation is just the square root of 4.24, which is equal to 2.059. So is that kind of simple enough? Just take the square root of the variance. You got it. So, and similarly, for the sample standard deviation, we just take the square root of the sample variance, which the sample variance was 5.3. So the square root of 5.3 is equal to 2.302. So, is everyone okay with that? Just take the square root of the number we calculated last time. So, the sample variance can also be found using the following shortcut formula, and you don't even have to calculate the mean. So the shortcut formula is S squared is equal to N times the sum of the xi's squared. So that means square every data value and then sum them up. Minus the sum of the xi's, this quantity squared. So I take all the individual data values, I add them up, and then I square them. Then I divide by n times n minus 1. And you don't have to calculate the mean. So you can also use the calculator to find these values as well. Did I show you all how to do that last time? So remember whenever we went on the calculator and I showed you that you can find the median on there as well? So you can find the mean doing the same thing. So we'll do that too. So I think I still have the numbers in here from last time. So go to stat. Let's make sure we have the numbers in. So go to edit. Those are the wrong numbers. So let's go back to this example right here. So you want to enter these numbers into a list So all you do is, wait, no, let's do this first so I can quit. Let's clear out that list. So go to stat, edit, clear list, number 4. Oops, can't see that. Then go second 1, and that'll take you to list 1. Enter, and it clears that list. You didn't have to do that. You could have just put it in a different list. It doesn't matter. So then I want to enter in those numbers. I hit 2, 4, 5, 8, 3. Everyone think they could enter the numbers in their calculator like that? Cool. So then go second, quit, and go stat, calculate. Gosh dang it, I keep going off the page. Stat, calculate, one variable statistics. So tell the calculator which list you have those values in. So I entered those values into L1, the first list. And then freak list, don't worry about this, just leave it empty, and then hit calculate. So, and it will tell you the mean, 4.4. It'll tell you the sum of the x values, so the sum of all those xi's. It'll tell you the sum of the x's squared, so it will tell you this piece right here, the sum of the xi's squared. Oh, that piece actually, the sum of the xi's squared. And also Sx right here, that is the sample standard deviation. So what do you think sigma x is? The population standard deviation. So, and then it gives you the 5-number summary, which we will talk about later. So, if you haven't started your homework yet, you will notice that the numbers on it are quite large for some reason. So, I'm going to show y'all an easy way to find the exact sample standard deviation and variance. So, has anyone in here used Excel? Okay, that's what we're going to use because it's easy to use. So, people online, I'll show you too. I just got to share my screen first. So, share your screen. Application window here. Okay, so now, say for instance, on the test score example we had, remember that one? It's on page 3. So, say for instance, we want to find the variance, but we want to do it on the computer. And why is it not taking my number? Frozen, unlicensed product, whatever that means. Lovely. Did they not have it on here? There it goes. So, type the numbers in. So you have 99, 86, 72, 98, 88. I might not be showing them. Sorry, I need to change this back. So you type in all the numbers. So 83, F off, 83. Why is it not doing it again? Well, it's not gonna freaking let me do it. So, stupid thing. Well, it won't let me do the rest of it because it's unlicensed, so they don't have the actual license for it, so it won't let me use it. So, if you want, you can actually do it in Excel. Then you hit the equal sign on your keyboard and you type var, so that's the variance. Then you open a parentheses and then you will select the data. So you just select all this. Then you close the parentheses and hit enter, and it would tell you the variance. So you enter in all the numbers you want into, I just put them into one column because it's easier. Then you go down to the one below it. So say I have all my numbers entered in here. Usually I just go down to the one below. then hit equals, and then type var, which is the function for variance in Excel, and then select the data values. So you just select those. And then close the parentheses and hit enter. If you have a MacBook, I don't think Excel is already on there, so you may have to download it if you want. You can get it for free from the Software Distribution Center through OSU. You'll get all Microsoft stuff for free. Or you can just go to your email, your like Outlook email, and if you go to the home page like of Outlook, you can download everything from there too. No. Did everyone online hear that? Because it won't let me finish typing. Okay. If I have time, I may post a video this weekend or tomorrow, and I'll show you how to do it on my computer, which has Excel, which actually works. Because on your homework, it is very picky about you having the exact answer on the variance, and your calculator only goes to a couple decimal places. Where am I at? Okay, here we are. So, stupid technology. So, let's go out of here. Hide that. So, that's how you do it in Excel. Sorry I couldn't finish showing you because apparently the school didn't pay for it or something. So, that is a shortcut formula for finding the sample variance if you don't want to find the sample mean. But the sample mean is actually in here because remember that x bar is equal to the sum of the xi's over n. So the sum of the xi's is actually nx bar. So the sample mean is actually in there. It just hidden. You don't need to know that. Just a fun little fact. So, what if we wish to compare the standard deviation of two samples with different units of measure? So say we want to compare test scores and height, see if there's more variation within test scores or height in the classroom. You could do that using something called the coefficient of variation. So, for example, say I wish to compare the variation of age and GPA of the students at OSU. Because there are two different measures, units of measure, so GPA is just a scale from 0 to 4, and age probably anywhere from 17 to 23. So then, because these are two different units of measure, I cannot simply compare their standard deviations. That wouldn't make sense, really. So instead, we must convert the standard deviations into what we call coefficients of variation. To compare. So, how do we find these coefficients of variation? So, you will need the mean and the standard deviation. So, the coefficient of variation is the standard deviation divided by the mean expressed as a percentage. So, if we know that, then for a population, we have the population standard deviation, CVAR, let's do this, equals the population standard deviation divided by the population mean. If I want to express it as a percentage, what do I do now? So now it's in decimal form. If I want to express it as a percentage, I need to multiply by 100. So, similarly, for a sample, I take the sample standard deviation, S, divide by the sample mean, x bar, and I multiply by 100. So it's the same thing in both cases. A standard deviation divided by the mean times 100 to get it as a percentage. Just the symbols change if you have a sample or a population. So does that make sense to everyone? Okay, let's see if you can figure out the example, and then I'll walk around and see if y'all need help. And then I'll go over the answer. Everyone online, you can do it as well. let's go over it. So, most of you got it right. So, we want to find the coefficient of variation for sales and for commission. So, I did it like this. So, I had sales were up here. So, the mean for sales was equal to 87, and the standard deviation was equal to 5. So, then our coefficient of variation for sales is equal to 5 divided by 87, and we want to express that as a percentage, so we multiply it by 100. And that gives us 5.75%. So some of y'all had like 5.747. That is the correct answer. I just rounded to 2 decimal places. So then do the same thing for commissions. So the mean for commission was 5,225. The standard deviation was equal to 773. So then the coefficient of variation for a commission is equal to 773 divided by 5,225 times 100. And that ends up being 14.79%. So, did everyone get those? Or does everyone see how I got those? Cool. Okay, so using those two percentages, which one is more variable? So which one has more variation? The commissions, because the coefficient of variation is higher. So the higher the coefficient of variation, the more variation there is. So that means thus commissions are more variable. Meaning there's more variation in commission. So is everyone okay with that? Cool. So now we're on to section 3.3, which is about measures of position. So first thing we're going to talk about is percentiles, and then we're going to talk about quartiles. So we use percentiles and quartiles to locate the relative position of a data value in a data set. So for percentiles, we want to divide the data into 100 equal groups. So what it says in here is a percentile is a measure that indicates the value which below a percentage of the data falls. So say we're up to a certain data value, we want to know how much of the data falls below that. What's the percentage of it? That's the percentile. So, for example, the median in a data set is the middlemost value, meaning half of the data falls above the median and half below. This makes the median the what percentile? Yep, 50th. Because 50% of the data falls below it. So, say for instance, when I draw a number line, I have, where's my other pins? Stupid. There they are. So then, say I have the median is here, Then I have 50% of the data is over here, and the other 50% is over here. So, that makes sense to everyone? Everyone online, you following what I'm doing? Cool. Okay. So, to find the percentile rank, we want to use this formula. So the percentile rank is equal to the number of values less than x. So x is just the number we're going to find the percentile of. So the number of values less than x plus 0.5 divided by the total number of values since it's a percentile, we want to multiply by 100%. Okay, does that make sense to everyone? We want to find the number of data values that fall below a certain value. We want to take the number of values that are less than that certain value. We add this 0.5 because that's a correction factor. And then we divide by the total number of values. Okay, is everyone okay with that? Okay. So, the next thing we want to talk about is finding a data that corresponds to a given percentile. So, this is going to be a little different. So, the first thing I'm going to tell you to do before we begin is put your values in order. Ascending order, so from largest to smallest. Okay, and that'll help you. In a second, and you'll figure out why. So, we say that C is equal to N times P over 100. So, N represents the number of data values, so the total number of values. P represents the percentile. So, okay, what else? Okay. So, if C is a decimal, round to the next whole number, round up to the next whole number. And if C is a decimal, or not, if C is a decimal, if C is a whole number, find the value between C and C plus 1 by taking the average. I don't know why, it's just kind of a rule. What's up? Yes, I am so sorry. I zoomed it down whenever I did the thing. So I'm guessing if it's a whole number, this is kind of just like for continuous data. So to make that correction factor kind of show up here, we want to take the average of the two. Since we're rounding up to the next whole number on this one, so we're kind of overestimating it. So on this one, we're going to do the same. Does that make sense? Kind of. It's just one of the weird rules they have. So you're probably wondering, what the heck is this C? So C, I'll write it in a different color. C is an index. So whenever we have these values in ascending order, C is going to represent the number, like the number in the data set that corresponds to that percentile. You'll see in a second what I mean. So first thing we want to do is try it by an example. So we first want to find the percentile rank of 12. So the numbers are already in ascending order, so that's helpful. So then I'm just going to put PR as the percentile rank. So PR is equal to the number of values less than 12, so that is 2, plus the correction factor of 0.5 divided by the total number of values. So the total number we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, times 100 as well. So that is equal to 2 plus 0.5 is 2.5 over 10 is 0.25, and times 100 is 25%. So that means 25% of the data falls below 12. Okay, so now you'll see where this C comes into play. So find the value corresponding to the 75th percentile. So first I want to find which number in the data set it's going to be. So that's going to be the C index. So then we have C is equal to NP over 100. So N in this case is what? So the total number of values, 10. So then we have 10 times 75 divided by 100. Does anyone know what that equals? Ten times 75 is 750. Divide that by 100 and I get 7.5. So using this first rule, if C is a decimal, round to the nearest whole number. So, oh, you can't even see it. So we'd round this up to 8. So then what I want to do is find the 8th number in the data set. This is why we order them, that way you can count up. So we have 1, 2, 3, 4, 5, 6, 7, 8. So this is the 8th number in the data set. So the value corresponding to the 75th percentile is 20. I need to make this thing longer. So then the next thing we're going to do is find the value corresponding to the 60th percentile. And that'll kind of illustrate this second rule. So what we're going to do is the same thing. So C equals NP over 100. So we have C is equal to 10 times the percentile we want, 60, divided by 100. So that equals 10 times 60 is 600, divided by 6 is 6. So that means using this rule, we want to find C and C plus 1 in the data set. So we want to find the 6th number and the 7th number and then average them. So the 6th number is 1, 2, 3, 4, 5, 6. So it's 17. And the 8th number is 18. Or the 7th number is 18. So that means we want to take 17 plus 18 and find the average. So if you do that, that's 35 divided by 2 is 17.5. So the value corresponding to the 60th percentile is 17.5. What's up? Like that? A little bit more? that good? Sorry. The way this thing is set up is I can only push it up so far before it hits this thing. So it's a pain in the butt. But turn it off, light. Okay, does everyone have that? Okay, the second rule is kind of weird. It's just to make up for this correction factor that we have whenever we find the percentile rank. So we just add this correction factor on, so we have to account for it in this right here as well. The reason we add this correction factor is because we have a countable number of values. So that means we have a discrete number of points. So our data is discrete. So that means if we want to approximate it with percentiles, we're going to have to make it continuous and add on that correction factor. That will not make sense until we get to discrete and continuous distributions. Just remember those two rules. You'll be fine. So that's how you find percentiles. The next thing we're going to talk about is quartiles. So if percentiles broke the data into 100 equal groups, so each representing a percentage, then what do you think quartiles will do? Yep, so it's going to be 4. So quartiles, quarters, how many quarters in a dollar? 4. So it's going to divide it into 4 equal groups. So remember how I talked about the 5-number summary that your calculator gives you? Whenever you do one variable statistics, this is where it comes up. So Q1, the first quartile, so this is going to be called the 25th percentile. So if you have 1/4, then you have 25% of a dollar. So that means the first quarter is going to be your 25th percentile. Then what would the second quarter be? The second quartile? 50th. So if you think of this, then what is Q2 going to be if we look at the previous page? Where was it? There it is. So if Q2 means it's the 50th percentile, then what does Q2 equal to? The median. So the median is the 50th percentile. Q2 is the 50th percentile. So Q2 must be the median. And then Q3 will be the 75th percentile. So to calculate the quartiles, we can use the percentile formula from page 12. A simpler way to calculate quartiles is to use the following method. Okay, so first we want to arrange the data. Excuse me, I'm so sorry. So arrange the data values in order, so ascending order again. Find the median, which I told you is Q2. Oh wait, this will kind of illustrate it better. Let me draw a little thing first. So here we have a number line. So this one right here represents the minimum. This is the max. So we have, say for instance, the first quartile here. So this is Q1. So that means that this right here is equal to 25%. Say for instance, here we have Q2 or the median. And this is another 25% in here. Then we have Q3 up here. That's another 25% here. Then the maximum is the largest data point we can have, so all the way up to here. From the minimum, we have 100%. All the way from here to here is 100%. So that's how you do it. So first thing we want to do is find the median. And then next thing we want to do is find the median of the data values that fall below Q2. So if we have from here to here, the middle value in there is going to be Q1. Same thing we're going to do on the top end. So we have the number of values that fall above the median. So we're looking at this side. We want to find the middle of that. That's Q3. Okay, so first thing we want to do now is define something we call the interquartile range. So the interquartile range, which we call the IQR, is equal to the difference between the third and the first percentiles. So that means IQR is equal to Q3 minus Q1. The third quartile minus the first quartile. Is everyone okay with that? Okay, so now we want to try an example just to illustrate this. So it says 11 major earthquakes had Richter magnitudes as shown below. Find the quartiles and calculate the interquartile range. So the first thing we want to do is put these values in order. So if you do that, we have 5.4, 6.2, another 6.2, 6.4, another 6.4, 6.5, 7.0, 7.2, another 7.2, 7.7, and then 8.0. So that's just putting the values in order. So the next thing we want to do is find the middlemost value, and that will be Q2. So that'll also be the median. So let's see how many numbers I have. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n is odd. That means I will take the middlemost value. So you just take the largest and the smallest value, and then you work your way to the middle. So that means 6.5 is the median, or Q2. Okay, so now what I want to do is use this rule right here. Find the median of find the median of the data values that fall below Q2. So now what I want to do is see how many values are up here. So I have 1, 2, 3, 4, 5 data values below Q2. So I want to take the median of that. So again, n is odd. So I will take the middlemost value. So I go n, and I notice that Q1 is equal to 6.2. Okay, now I'm going to do the same thing for the upper end. Now, someone tell me what is Q3? 7.2, correct. So then I have that Q1 is equal to 6.2. Q2 is equal to 8.2. Oops, not that. Q2 is equal to 6.5. I don't know where I got 8.2 from. And Q3 is equal to 7.2. So if I have these numbers, then what is the IQR? Yep, 1. So I have Q3 minus Q1, which equals 7.2, minus 6.2, which equals 1. Is everyone okay with that? Okay. So if I don't tell you specifically to show me how you found the quartiles, you can do this. So go into Stat, Edit, just enter in those numbers here. It doesn't have to be in order. So 7.0, 6.2, 7.7, all the way up to the last one. Let's oops, that should be. Oops. Yep. Okay, so I enter those numbers into a list, and I'm going to do the same thing I did earlier. So Stat, calculate one variable statistics, tell it what list I have the numbers in, so it will be again an L1. And I press calculate, and here it tells me the minimum, the first quartile, the median, which is the second quartile, the third quartile, and the maximum. So it gives you all the numbers you need. The only thing it doesn't give you is the IQR, which you can find. So, is everyone okay with that stuff? Okay, cool. So, remember when we talked about how extremely high or extremely low values can affect the mean of a distribution? So, what are those extremely high or extremely low data points? We call them outliers. So, we want to figure out how to identify them. So, an outlier is an extremely high or extremely low value when compared to the rest of the data values. We can calculate outliers by using the IQR. So, by using the interquartile range. So, the way we're going to do that is any data value smaller than what the heck did I just do there? Q1 minus 1.5 times the IQR is an out. I'll just do this all in one. Any data value smaller than Q1 minus 1.5 times IQR, or Q3 plus 1.5 times IQR. This should be larger than. So if we have any data value that's smaller than Q1 minus 1.5 times the IQR, or larger than Q3 plus 1.5 times the IQR, is called an outlier. So, does everyone understand how I'm going to figure out if something's an outlier? What's up? Why 1.5? Just something they made up. I don't know why. I'm assuming probably, I don't know, to be honest. It's just the rule they've always had. I don't know. You do like to ask questions, which is good, but I don't know the answer. That's what we've always been taught. I guess what they probably did is they wanted to figure out what's the maximum or minimum value you can get without it changing the mean too much or changing the performance. So say we have a machine and we want to see how it runs compared to other machines. So we're going to run 100 machines and we're going to see which one is extremely good or extremely sucks. And then they came up with a cutoff somehow. We want to take 1.5 times the machine that runs 75% better than the others, and then 25% better than the others. That's my guess. It's probably something that came up by algorithm. So, something that's above my pay grade of a GTA. So, using the example above, are there any outliers in the data set? So, we had that Q1 was equal to 6.2. Q2, which is the second quartile, I don't even need Q2, I think Q3. Q3 was equal to 7.2. And we already found the IQR is equal to 1. So then what we're going to do, so Q1 minus 1.5 times the IQR. We want to see if there are any data values smaller than that. So what's Q1? 6.2. And I want to subtract off 1.5 times the IQR, which is 1. So that gives me 4.7. So we look at the data set, and are there any data values smaller than 4.7? Nope. The smallest one was 5.4. So no data values less than 4.7. Okay, then we're going to do the same thing to the upper end. So we have Q3 plus 1.5 times IQR, which is equal to 7.2 plus 1.5 times 1, which equals 8.7. And we see, are there any data values larger than 8.7? And the largest we had was 8.0, so no, there are not. So no data values greater than 8.7. So what do you think that means about our data set? So there are no outliers in the data set. So, what's up? Yep. Yep. I believe in the homework, it asks you to identify if there are any outliers. So you just see what numbers are greater than this cutoff and lower than that cutoff. And you just say that whatever numbers are lower than that smaller one or greater than the upper one. And that would just tell you the outliers. So could you move the page up? Will the problem be an even? Will the problem ever be an even number of data points? And if so, how is that calculated for quartiles? Sorry, I did not see that question until now, Blaine, but I usually use an odd number. But if you do have an even number, you're going to go about it the same way. So let's give an example. So I'm just going to make up some points. So we have 2, 3, 5, 8, 10, so 1, 2, 3, 4, 5, and 13. So say I have this data set here, and I want to find the quartiles of it. So what I want to do first is find the median of it. So n is even, so I'm going to have to take the average of the two most middle values to find the median. So then doing that, these are the two most middle values, 5 and 8. So if I want to find the median, I need to take 5 plus 8 over 2. and that'll be 6.5. So that tells me my median is equal to 6.5. So is that making sense so far, Blaine? Okay, so now you want to find the median of the data values that fall below the median and above, and that'll be Q1 and Q3. So the median of the data values below the median of 6.5 is going to be, so average 2 and 3, and that'll be 2.5. And I'm going to do the same thing up here. So I take 10 plus 13 and divide it by 2. So that'd be 11.5. So does that make sense? I'm going to see how your calculator would do it and compare. So 2, 3, 5, 8, 10, 13. Okay, so your calculator is actually going to do it a little differently if it's even. So we look at the numbers that are less than this median of 6.5. So less than that median of 6.5 would be these three numbers here. So n is odd, so take the middle one. So that'd be Q1 equals 3 then. Does that make sense so far now? Okay, and then for the upper end, we're going to look at the numbers that are greater than 6.5, and it will be these three. So then, since n is odd, I take the middle one, which is 10, and then that means Q3 equals 10. Okay. I couldn't remember if your calculator did it this way or that way, so I checked. Hey, what's up? What's up? On your test, if I put one on there, it'll be an odd number, so it's easier. So I usually pull stuff from the notes, and I may just change the numbers. So usually I keep it consistent with what the notes is, and it's usually odd, so it's easier. Does that make sense? So if an even number pops up on the exam, just use your calculator. It won't pop up on the exam, though. But if you see it on the homework, that's how you should do it. Just do it on your calculator. So that's a lot of stuff so far. So the next thing we're going to talk about is section 3.4, and that's explanatory data analysis. So we're going to be explaining data sets using something called a box plot. So recall in chapter 2 how we learned to visually explain a distribution with histograms, frequency polygons, and all that other crap we talked about. So now we're going to talk about a box plot. So anyone seen a box plot before? It's not that exciting. It's just a box with whiskers on it. So for box plots, we let the median be our measure of the center. Who dat? No, I don't want to join the honor society. So, and the IQR be the measure of spread. Do y'all think next chapter I should bring in a basketball to explain probability? I thought about doing it. I mean, I suck at basketball. I haven't played in a couple years, but it'd be fun. Since there's barely anyone in here. Quit calling me spam numbers. Everyone keep getting the, you want to renew your auto warranty calls? How the heck did they get my phone number? Weirdos. So, let's go over this again. So, for box plots, the median is going to be our measure of the center, and the IQR will be the measure of spread. So, the IQR will be the length of the box. We'll show that in a second. So, In order to draw a box plot, we must first know the 5-number summary, which I just talked about. So the 5-number summary is the minimum, the first quartile, the second quartile, the third quartile, and what do you think the last one is? The maximum. So those are the 5 numbers you need to create a box plot. So here are the steps for constructing a box plot. So first, you want to find the 5-number summary. So you just find what these are. Usually, the easiest way to do it, your calculator will do it for you. It'll tell you the minimum, first quartile, the median, the third quartile, and the maximum. So that's the easiest way to do it. So second step, draw a horizontal axis and place a scale on the axis. So the scale is going to depend on how spread out your data is, but usually in this class, I make it pretty easy. So remember, spacing is important. That way you have equal, like say you have test scores and you want a spread of like 2 points for each thing. You don't want to make 3 points all of a sudden, because then it's going to make it look like some people scored higher than they actually did. So that's kind of why. So locate the lowest data value and the highest data value and draw a dot. Next, locate Q1, Q2, Q3 and draw a vertical line. So this is not going to make sense until I draw one. So here's an axis. I have the minimum here. So the minimum, the first quartile here, so Q1, second quartile here, Q2, third quartile here, Q3, and I need to make it a little longer. And then I have the maximum up here. So the first thing I want to do is locate the lowest and the highest data value and draw a dot. So I want to draw a dot at the minimum and the maximum. So a dot there, a dot there. So next, locate Q1, Q2, and Q3 and draw vertical lines. So vertical line here, here, and here. Connect the lines to create a box. So I literally connect the top ones and the bottom ones to create a box. And then finally, connect the lowest data value and the highest data value to a box by drawing a line. So I draw a line from the dot to the box on the lower end, and the same thing on the upper end. And that's a box plot. Pretty good stuff, you know, pretty boring. So note, if outliers are present, they're represented as dots before the minimum value or after the maximum value. So, for example, first we want to put a little note. So, in this case, if outliers are present, the min slash the max, in this case, are the smallest slash largest, so it all depends on if it's the minimum or the maximum. Data values that are not outliers. So to illustrate that, we're going to draw another thing. So draw a little longer one. So say, for instance, I have my minimum is right here. I have Q1 here. Yeah, sorry. It's hard to write like from over here, this angle, because I'm right-handed, but we'll try. So, and then Q2 is here. Q3 is here. Oops, why am I putting an 8? Q3 is here. Say the max is right here. And then I have some outliers out here, right here. So then for the minimum, so I'm going to have literally the same box plot as above. It's just these 4 points out here are outliers. And this minimum value right here is the closest data point to the outlier, like the next smallest from the outlier. Does that make sense? So say, for instance, if this outlier was a point, say, -1.5, this would be the one above it, like a little larger than it. So this would be negative like 1.3. So say my outlier cutoff was at -1.4. That any data value less than -1.4 is an outlier. So these two would be outliers. And this one, -1.3, would be the minimum value because it's the first data value that is not an outlier. Did that make sense? So, and then I still have the same thing here, little box thing, and then the whiskers. So all of these points here, this one, this one, this one, and this one are outliers. Is everyone okay with that, or do we need to explain that again? Okay. So what's next? So we'll go over this, and then we'll probably get out. So what do box plots tell us about the distribution? So if the median is in the center of the box plot, so the box plot looks like this, so I have that. Like that, and the median is right here. So if the median is in the center of the box, the distribution is symmetric. So if the box plot is, if the median is closer to Q1, first remember that this is the median. The second one, so this is Q1, that's the median, that's Q3. So if the median is closer to Q1, so it looks like this, then the distribution is right skewed. Does anyone want me to illustrate why that is? Okay, so say for instance, so this is the median, so that means that about 50% of the data falls below that, about 50% above. So that means my distribution would look like that. So I have 50% of the data right here, and the other 50% up here. But if you look at that, there's a little tail on the right side, so it's right skewed. That kind of illustrate it and make it kind of clear. Okay. Similarly, if you're doing for this, so the median is going to be right in the middle. So that is symmetric. So, and then if the median is closer to Q3, then what do you think will happen? Yep, correct. Okay, so and to illustrate that, so the median is up here, so that means 50% of the data is going to fall below and 50% above. So it's going to look something like that. And obviously, that is left skewed. Okay, so on Tuesday, we will finish up the chapter, and then we'll talk about probability. So I would probably get started on your chapter 3 homework. I think, did I open it yet? Okay, so if I did, then get started on that. It's probably going to be a lot of this stuff. If y'all have any questions about how to use Excel or anything, since it kind of didn't show in here, let me know. Or if you have any questions, just email me or stop by my office. Come on.